Welcome to the video on variance. So before we get started with the actual calculation of variance, I want to briefly discuss the equation and then how the equation differs between the population and the sample. So down here on the bottom, I'm just going to start with what we call parameters. And parameters represent the population. And so when we think of the mean of the population, what we don't call when we're talking about the population, the mean is not referred to as an x bar, it's referred to as mu. And the variance of the population would be sigma squared. And then the standard deviation of the population would just be sigma. And then when we have these things called statistics, these are based on the sample that comes from the population, and they're our best estimate of what's actually happening in the population. So the mean we denote as x bar, the variance has now become s squared, and standard deviation becomes s. Okay, and so when we're thinking about the actual variance, when we think of it from a population standpoint, the equation kind of starts out as, sigma squared equals the sum of the xi minus x bar squared divided by n. And so this top piece, this numerator, we'll just kind of circle here, this numerator is really this fourth column here. So it's these squared deviation scores, and then we're dividing by n. And so we're getting a mean. So another way to think of variance, this can be variance. Another way to think of it is the mean of the squares, or mean squares is another way that you might see this represented. And so that's all it is. It's just taking all these squared deviation scores, summing them together, that's our numerator, and then dividing by the total amount of observations that we have. Okay, I guess to be a little bit more accurate here, I just realized I did this. I'll go in and erase this piece right here. I didn't use the actual parameter here. You may have already caught that. The parameter from, because I'm using the sigma squared here, this should be, I did it in red. Maybe we'll go back to yellow. This should be mu here. Okay. And then how does this equation change when we move over to the actual variance statistic estimated from a sample? Well, the sigma squared becomes s squared. Now this is still sum, and it's the xi minus this time x bar squared, and then we're going to switch from a total observations to what's called n minus 1. This n minus 1 is referred to, well, you might see the Greek lowercase letter, it looks like a V, it's called nu, pronounced nu, and it is the degrees of freedom. We'll talk about that in just a minute, but we have to understand is that, as we're starting to, use the mean to estimate, this mean here, the x bar, to estimate this over here, the parameter, we keep subtracting the raw scores from this x for the n amount of deviation scores that we're going to have. And what happens is the sums of squares, the total of this column right here, are sums of squares, right, which is 66 in this particular case, starts to become biased. And so the way that we unbias it, it starts to become biased in it's biased, by the way, because we don't actually know what this mu value is. It's unknown. And so when you're using the x bar to actually estimate, what will happen is you won't get the exact variance of what you should have gotten had you have known this mu value. And so this sum over here becomes biased, and the way that you unbias it, and it just happens that precisely how much you have to unbias it by is this value right here, the degrees of freedom, that if you actually were to divide by n minus 1, so your total amount of observations minus 1, it actually corrects for the bias that occurs, and now you get an unbiased estimate of the variance here, which is s squared. It's interesting how that happens, more for a different video and a different time. So let's take this equation then, and then let's just kind of put this in. So our variance then becomes s squared equals our numerator, which is the sum of the xi minus x bars. That's this fourth column here, which is 66. And then we're going to divide by n minus 1, and so our total n observations is 10, minus 1 is 9. And so what this will give you is a value, if you plug and chug those numbers, of 7.33. And remember that all your measures of variability, as well as your measures of central tendency, are going to carry the units. So this variable here, this random variable x, which is years of employment, still carries with it its actual years, which makes a lot of sense, because if you take years and then subtract them from the mean years of, which was 6, then you're going to get a deviation score in years, and then you're going to get something odd. You're going to get years squared, which isn't interpretable for us. And so in this particular case, what do you have? S squared, this is actually 7.33 years squared, so this is actually not interpretable for us at this point. And so what we'll have to do, and this is going to give you some intuition, thinking forward to standard deviation, is now we need to have something that's kind of a little bit more interpretable for us. And that is the video on variance. Thanks for watching.